Did you solve the problem? Furthermore, did it match these answers? I hope not, actually. This one, I hope so. This one, you might encounter a different answer if you did it the way we would expect to do it on paper. So let me show you what I mean. First, we're going to do test number 1, just to confirm this one. We'll go through it quickly, because I'm going to assume you give it a try. 2, 4, 6 pi electrons. Why am I counting those already? That satisfies Huckel's rule, and I would have said aromatic, but it's non-aromatic. So that's what happens if you skip to the last test. It doesn't even apply the number of pi electrons without doing the first test. Is it a planar ring? Well, I'll assume it's planar, okay. Is it delocalized? Well, it's a ring, but it's not delocalized, and here's why. Every single carbon is using a p orbital except this one. No skippies allowed. This carbon skipped. Doesn't get credit for being aromatic because it skipped. So just in case we missed that one, I'm going to circle that in red and say that's a sp3 carbon, not using a p orbital. So this had a big fat fail for the first test, which means you can't even go on to the second test. It cannot be anti-aromatic, it cannot be aromatic. Must be non-aromatic. If you did follow all the rules for the last one, you might have arrived at a different answer. Let's see why. Let's do test number 1 first this time. Ring, check. Every single carbon using a p orbital. In other words, it's conjugated, check. So it can be conjugated. All right, well then, let's assume it's planar because we don't have a 3D model of it right now. So I'm just going to put a check here. If planar. Let's move on. How many pi electrons? 2, 4, 6, 8. That does not satisfy Huckel's rule. That means it's a 4n situation, or n equals 2. So we can't add 2 to that because 2 times 4 is 8. So if you added 2 to 8, we'd have a 10 pi electron system. So this would make us think it was anti-aromatic. But our answer was not anti-aromatic. Our answer was non-aromatic. Well, the only thing that we could not address was if this was indeed planar or not. So because of the large ring size, it's kind of a hint that it's possible to actually still distort it out of the plane, even if it is going to have pi bonds, because those bonds connecting the 2 carbons that are making pi bonds are still sigma bonds, which you could rotate around. So I have a 3D Spartan rendering for you to see what cyclooctatetraene really looks like in 3 dimensions. So let's just did this one kind of quickly, but it makes all the difference in the world to see in 3D versus worrying about 2D sometimes. So let's take a quick look. And that's how we draw it on paper. But if we rotate it in or out of the plane, so it's zooming in a little here. And which way did I go? Oh, I went that way. Okay. So look at that. Wow, not even close to planar. Shaped like a tub, right? Kind of like a big, huge boat or a tub sort of shape. It's bent out of the plane. So that's enough to see that concept. So since it's not planar, we don't even pass the first test. So we know now that this is not planar. I'll put a red mark here. So it's actually referred to as kind of a tub shape. Now, would you have known that without the 3D models? No, you would have had to do some molecular modeling to arrive at that conclusion. So for that reason, when you're doing these problems, read the directions very carefully. It will either tell you what shape it is, or it will tell you to assume it's planar. If the shape is not a planar shape like a tub or a boat, that's obviously not planar, not all that carbon atoms can stay in the same plane, then you're going to rule out the second test. It has to be non-aromatic. But if it's planar, then you can apply all the other criteria and give it a check. Okay? Why is it tub-shaped? Why is it not planar? It turns out anti-aromatic is actually very unstable. So it intentionally folds to avoid being planar, because if it was planar, it would be anti-aromatic. And we'll understand that when we get to the orbital diagram. So that's not something we can comprehend just yet without doing that. But it turns out that anti-aromatic is the worst case scenario. It's very unstable. So if a molecule can adjust itself to not be anti-aromatic, it will do that. So notice the one that we did find so far that was anti-aromatic is a famous example. It can't do anything about it. It's very reluctantly, very hard to form something like this because it's actually very unstable. So like I said, we're moving on from benzene as our only case. There's lots of aromatic examples out there. Very stable. Aromatics, very, very stable. So we're going to see them pop up a lot in future chapters. So let's just take a moment to see the different forms aromaticity can come in. So everything in this box is aromatic. So it's not, but it's not benzene clearly. We could have polycyclics. So let's circle the polycyclics. That means the rings are either connected or fused. So these share sides, so they're fused. So notice the pi system. We can go 2, 4, 6, and I'm going to keep going and make a giant ring. 8, 10, 12, 14. So I can imagine, even though there's 3 6-membered rings, it's possible to say, oh, that ring's aromatic, that ring's aromatic, that ring's aromatic, or you could actually look at it as a whole ring and see if it can also be aromatic that way. If it can be aromatic, you're going to pick the way that makes it aromatic. So notice I have 2, 4, 6, 8, 10, 12, 14. We're going to assume all of the other criteria because I told you it's aromatic already. We're just proving that the electron count adds up. So 14 pi electrons does actually add up to 2n plus 2. Now, how does this one, this is actually called anthracene. And so I'll give you the names of these since they're really common. This one's called azulene. And notice that it's another fused ring system. And if we were to try to count the rings individually, 2, 4, it'd be kind of confusing to know what to do with this one, which is why it helps to go around the whole perimeter. 2, 4, 6, 8, 10. 10 pi electrons is a 2n plus 2 number, or 4n plus 2 number. Okay, let's look at the ions next. I'll circle those in blue. Ions, cations and anions, can be part of an aromatic ring system. So this guy is basically this one that was non-aromatic, 7-membered ring. Let's draw it out. Those are always fun, right? My trick for drawing a 7-membered ring is to try to start drawing an octagon, because those are easier, and then just change what would have been a side, the last final side here, change it to a vertex here, point. That way it doesn't come out too atrocious. Okay, so what this circle means is that we have exactly this, but a delocalized positive charge. So instead of having a skipped atom, which is not using its p orbital, we have one that is using a p orbital, it's just empty. Because remember that carbocations are sp2 hybridized. C plus is sp2. What does that mean? It's using 3 sp2 orbitals plus the leftover p. It's empty. It's an empty p orbital, but it's still there. Can electrons go in an empty p orbital? Yes. We can delocalize electrons into an empty p orbital as well as a full p orbital. So they have to move out again. That's why the conjugation is important. But we're allowed to use empty orbitals. So sp2 hybridized, so empty p orbital available for delocalizing. So that's why that one actually, delocalizing would be a better way to phrase that. So that's why we can denote it as a circle, because it's delocalizing that positive charge. If you draw those resonance structures, you'll see that. So the total pi electron count is 6 pi electrons, 2, 4, 6. That's just like benzene. We know it's planar, cyclic, no interruptions with p orbitals. Every carbon's using a p orbital, therefore aromatic, because it matches the 6 pi electron. How does it look when an anion does that? Let's look at a carbanion this time. Remember a carbanion? opposite a carbocation, it actually has a lone pair, a filled p orbital. So it's going to use a lone pair, p orbital for the lone pair if it benefits that molecule stability-wise. So remember, p orbital is actually a little higher energy than a hybrid orbital. However, if it can add conjugation and possibly aromaticity, then it will certainly let that orbital be, that lone pair occupy a p orbital. So let's write that out. Actually, I'll just even draw the p orbital because that would actually be lone pair in p orbital. Since we're drawing p orbitals, why don't I draw the one from the carbocation there? So that's a filled p orbital. This is an empty one, but we can delocalize the filled p orbital, and that tells us we didn't have any skipped atoms now. So we're satisfying condition 1. It's cyclic, it's flat, planar, parallel p orbitals on every single adjacent carbon, no skips. So take that into account. We're ready to do electron count. Lone pair counts as 2, pi bonds count as 2. 2, 4, 6, 6 pi electrons. You're going to have a ton of others to do, so I want to try to give you a little flavor of the other varieties you'll see, because your homework will be doing like a rapid amount of drills of identifying which ones are falling in which category. So this is just the tip of the iceberg here. But the other ones you'll probably encounter quite often is heterocycles. Where do they come into play? Remember, heteroatoms, when they're part of the ring, their lone pair may or may not contribute to the delocalization of the electrons. So let's look at that. And I'll also give some names for some of these, because these are all famous examples that I'm giving you. So this is the tropylium ion, the one that was the 7-membered ring with a positive charge. We'll see a lot of that later. And this is the cyclopentadienyl anion. And you can actually write it like that as well to show that it's delocalized with a negative charge on any one of those carbons. Alternating carbons, actually. So cyclopentadienyl. This is furan. We know about that one. Relative of tetrahydrofuran. And we have 2 lone pairs on oxygen. And if we said, what's the hybridization of oxygen? You'd say, well, we have a nearby p orbital that's filled. It has a chance to be conjugated and possibly aromatic, but we know that we can't be aromatic unless that lone pair is conjugated. So let's let it be. That means we're filling a p orbital for one of the lone pairs. The other is not in a p orbital. It's going to be in a hybrid orbital. So this one would be in whatever the hybridization is. So if it actually is using a p orbital, you take one out of the equation. We have 3 orbitals left, spp, so it's an sp2 hybridized oxygen. So it's using sp2 orbitals for all those other bonds. Now, if we let that lone pair occupy a p orbital, it counts as the pi electron system. So are we ready for test number 2? I think so, right? Because we have, if we allow that to be a full p orbital for that lone pair to be in there, then we have a p orbital on oxygen, p orbital, p orbital, p orbital, p orbital for those carbons making pi bonds. No skips, so we have a continuous cyclic arrangement of p orbitals being used by every atom in the ring. Now we're ready for test 2. Test 2 says, what's the electron count? 2, 4, then you count the one that filled the p orbital, 6. So of course it's aromatic. We know these are all aromatic, but I'm just showing you how you will have to be able to account for the electrons in different ways. This is called parole. I'm not going to repeat. You might want to practice that same analysis on your own with this one, because it's the same idea as furan. Okay, this one, 2 nitrogens, imidazole. Okay, so how do we count these? 2 heterocycles can have multiple heteroatoms. So we know we need to do that count because otherwise we'd have an atom that's skipped. However, this nitrogen's already making a pi bond. So yes, it has a lone pair, but is that lone pair in a p orbital? No, because the p orbital is being used for the pi bond. So if I asked a different question, which is what orbital are each of those lone pairs in, we would answer as follows. Say this one's in a p orbital. And then we'd say this one is not in a p orbital. It's in its hybrid orbital. It's using an sp2 hybridized orbital. Why is it not in a p orbital? Because we don't need it to be. We've already used the p orbital. P orbital is being used by nitrogen. It has a filled p orbital, part of the pi bond. That's a common source of confusion because you kind of just want to have every lone pair occupy a p orbital, but that's not the case. This is not in a p orbital. The p orbital is used right here for that pi bond. That nitrogen is overlapping with that carbon's p orbital by having a pi bond. So there's no skips now. P orbital on nitrogen being used, p orbital being used, p orbital being used, p orbital being used, p orbital being used. So we satisfy test number 1. It's planar, cyclic, no, it's continuous. Delocalization of electrons. 2, 4, 6. Thank goodness we don't count that blue one because then we'd have 8 and that would be anti-aromatic and we know it's aromatic, right? So yes, that does not count in the electron count because it is not part of the pi system. 2, 4, 6. 6 pi electrons. So let's look at a similar one, pyridine, which is a 6-membered ring, benzene with one of the carbons replaced with a nitrogen. Same story. Lone pair is not part of the pi system because that nitrogen's already made a pi bond. It has a filled p orbital already. It's not going to do it again. That's actually higher energy. That's why it won't do it again. 2, 4, 6. 6 pi electrons. We do not count the lone pair for this count. So sometimes you count it, sometimes you don't. You've got to look at each structure and evaluate it separately. It's not something you can memorize. You've got to apply whether it's beneficial for it to be in a p orbital or not. Okay, I hope that helps. We have some fun parts to get to next, which are some really cool consequences. So the fact that we have this incredible stability means that we actually have some different functions that arise from the fact that a material is made up of aromatic compounds. So we're going to learn a new attractive force that exists specifically in these type of compounds, and that helps explain some of their bulk properties. Since aromatic systems must be planar, they actually have a lot of surface area when they are kind of trying to, when we talked about van der Waals forces back in like chemistry 211 or organic 1, more surface area you have, the more stacking you could have, right? So if something is planar, you can really stack and optimize the surface area interaction. So that's like a high level of a van der Waals interaction. It has its own name when it comes to aromatic compounds because you have this polygon that's planar stacking with another one, making this kind of sandwich almost, but it's not perfectly. It's a little bit offset like you see here. And we can just highlight it and you might see it illustrated like that. You don't have to overlap all the p orbitals perfectly or anything like that. They're just offset slightly because of repulsive forces between the p orbitals themselves. So they're offset a little bit, so they're not a perfect superposition. They're like offset just like that. And so that's called pi-pi stacking. And we can abbreviate intermolecular forces, IMF, via pi stacking interactions. So that green is pi. You could spell it out, or you could just write pi. So that's an attractive force. It increases their ability to aggregate. So remember, more intermolecular forces, so if you increase them, it causes them to stick together more, which changes its bulk property. It can have a higher melting point, boiling point, viscosity, right? So also something called tensile strength, how strong it is. It really sticks. So tensile strength is something, if you stretch it, you can actually measure and quantify it. If you stretch it, what force is required to break that item. And so that is a bulk property that we see on the macroscopic scale that relates to something on the nanoscale, like what's going on with those molecules. Why are they so attracted? Why is it so hard to break the material? It has to do with their attractive forces. So we see that sort of trait come into play with compounds that have a lot of like polycyclic aromatic hydrocarbons. We're going to start with the most famous one. You probably have studied this extensively in bio, and in fact, you might have heard of pi-pi stacking interactions. But usually, I don't know about you, but when I first had my bio class, my first image of DNA was really more of a cartoon, just like kind of ribbons kind of intertwined, and I didn't really appreciate the complexity offered by DNA. Very amazing molecule, really. So I have a 3D model here, and if you take a look, you can see that double helix. And I'm zooming in because our job in biology, you're looking at what DNA goes and does, but in chemistry, we zoom in and we look at what is happening at the molecular scale that allows DNA to form that way, and what makes it so thankfully resistant and stable. So if we zoom in further and further, we get to the atomic level, what's going on, and the molecular components. And so we know that here we have, you might have looked at the hydrogen bonding before between the base pairs. And so you could see there's hydrogen bond donors and acceptors. And we're not going to spend too much time on that because that's kind of been done. But it is an important feature, that hydrogen bonding, to help line up complementary base pairs. But that's to get the two strands together. There's also a reason it folds the way it does, and it twists. And look at that even spacing between them. That is evidence of pi-pi stacking interactions. That could only happen if all of the base pairs were aromatic. Let's take a look. So what would you describe? Let's see, I don't know if you've had to memorize any of your base pairs yet. I always found it helpful to kind of look at the molecular features and try to find something in common. So this 5-membered ring we've looked at sort of like an imidazole, right? And we have a 6-membered ring fused to it. And notice we have 2 that have that pattern. And these 2 that have that pattern, where are they different? One has an amine branched off here. Well, this one has an amine branched off. This one has a carbonyl. This one doesn't. The other 2 are not 5-6 fused ring systems. So this is a 5-6, excuse me, I did it the opposite way. We put it in blue anyway. 5-6, 5-6. 5-6 fused ring systems. So this is adenine, and this is guanine. So adenine likes thymine. Now thymine is this last one here. And guanine is like adenine. It wants a 6-membered ring to kind of pair with because it optimizes its hydrogen bonding, and that's cytosine. Now, are these aromatic? Well, let's look at the ring system. We know they're planar. We see the 3D structure below. They're making perfect little stacks, right? So they're planar. Is there continuous use of p orbitals? So this lone pair could be using a p orbital. 2, 4, 6, 8, 10. Those lone pairs will not be using p orbitals because that nitrogen is already using its p orbital for the ring. It's gone. It's not available because we don't want to over-hybridize it. So 2, 4, 6, 8, 10. 10 pi electrons. That is a 4n plus 2 number. Yes, it's aromatic. how are we going to do the next one? This is kind of an interesting case. We have a lone pair right here. So we're going to do the same thing as we did in the previous one. This, however, must use its lone pair, whereas the previous one didn't because it wasn't making a pi bond. How do we handle this though? Because this is also using a p orbital, but its pi bond is external to the ring. So notice, even though this one was conjugated, for example, this lone pair is conjugated pi system is actually 12 electrons long, 2, 4, 6, 8, 10, 12. That's not in the ring, so it does not count for evaluating aromaticity. That would be a different question. If I said how many atoms are conjugated to each other, I could say 12. 12 pi electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Should I count that 9? Nope, 9 and 10. So 10 atoms conjugated to each other. How many electrons in the conjugated system? 12 pi electrons. How many in the aromatic system? 10 pi electrons, because these don't count. They're not in the ring. So if you don't count ones outside the ring, how do we handle this? I need this to be a filled p orbital. I need this to be a filled p orbital. So the easiest way to treat one like this, where it's like half in, half out of the ring system, is to see if you can draw resonance and reason it from there. So yes, I have a lone pair next to a pi bond, and I can draw resonance that allows, let's just draw, let's draw it up here. So I have my 5-membered ring, 6-membered ring. My oxygen is now singly bonded with a negative charge on the O. I could put all those lone pairs on there, 3 lone pairs. Double bond from my new resonance result. Positive charge here, yes, it's a Zwitter ion, but remember, sometimes the answer is in the Zwitter ion. And same as usual business over here. Okay, let's try, oh, missing one pi bond. Let's try again. Count the pi electrons to confirm it's aromatic. I want that lone pair there too. 2, 4, 6, 8. Skip anything outside the ring, 10. But I'm able to do that without skipping any atoms as well. So I didn't have to go outside the ring, and I confirmed 10 pi electrons. 10 pi electrons is indeed satisfying Huckel's rule. So yes. So if you get that tricky situation where you can have a hard time seeing if something's half in and half out the ring, draw some resonance so that you can separate it. Get some in the ring, some out. So you will encounter that here and here. So I'm going to leave those for you to try. I'm going to tell you the answer. Yep, aromatic. You tell me the number of pi electrons. So give it a try, and you can always check your answer with me later. Now we confirmed aromaticity, and the big consequence of the aromaticity is that it's planar, rigid, and allows for the pi-pi stacking. So where does that happen?